So yeah, what I was saying, I was just, basically I said not much more than what's written on the board. This theorem is what we're going to try to prove by the end of class next time. Okay. All right, so let me just make some quick remarks. Just make some
There's a question, Ellie, about
yeah.
since we're trying to do a supervised learning problem. At the end, like some of these parameters.
This is for,
they're
yeah,
different.
that's right.
And so
This is for a particular parameter. So choose a parameter, and it turns out that this condition is not too strict in the sense that it's satisfied for all but a measure zero subset of your parameter space. That was one of the remarks that I was just about to make. But away from that measure zero set, you can do this.
So let me ask a naive question, like just to like solve, to find our function that we're trying to learn. Do we need all the information, or does being able to compute this, like say, like you need this one parameter, this one? Is that part of
Right, so
for to answer the overall question?
right, so I haven't said anything about how this might relate to learning, but here's one thing that you might want to use something like this for, is that you have some labeled data set and you want to kind of understand what the topology of that data set is, or how the different, yeah. So then you might train a network to learn, if it's a data set that's labeled for a binary classification task, then you might train it to learn that binary classification. So then this with output, you'd have a single output neuron. And then what I'm claiming is that you could actually kind of compute the homology groups of the yes region and the no region of that binary classification task, and also see what's happening beforehand at the end of training, once it's classified. But right now, I'm not saying anything about training at all. This is just, it's a single parameter, and I'm just claiming that there's an algorithm for computing the homology groups of all of the intermediate decision regions and boundaries. Okay, so let me just write down some remarks so that you have them in your notes. So, first of all, so remember I had this notation for the pre-activation output of the ith neuron in the ELF layer. Then these are what I'm calling the decision regions. So for the I mean, this is slightly different from what I was saying before. Before I was not closing off the decision regions, but I'm going to do this, and in fact, this was sort of the source of the confusion that I had when Melanie and Sophia asked me to clarify this offhand comment I made about like certain labelings being non-unique. It was precisely because of this. So somehow I should have formalized things to start with rather than kind of being informal to start. Anyway, these are the decision regions, and the pre-image of 0 is the decision boundary. And the point is that all of these, because these maps are continuous, all the maps are compositions of continuous maps. So they're continuous. So the pre-image of a closed set is closed. So each one of these is a closed set. These are all closed subsets of the domain. And the second thing I'll say is that generic and supertransversal are geometric conditions. Natural geometric conditions. On the locus of nonlinearity of this finite PL map. We have this overall finite piecewise linear map from the domain to the codomain of this ReLU neural network function. And I'm gonna get clear with you about what these conditions mean. But for now, just think there's some natural geometric conditions. And then the other thing that I want to write down that I said is almost all, i.e. away from a Lebesgue measure 0. Subset of parameter space. Parameters are generic and supertransversal. So we are able to compute the homology groups for almost all of these maps. And the condition where things fail is an easy, not easy, but like a natural condition to state. Okay. All right, so what's going to be necessary is for me to formalize everything that I was saying sort of informally last time. And it might be, might feel like a little bit much at first, but it's actually, it puts things into a really, really nice framework, I think. I should pause for questions. Yeah.
With this locus of nonlinearity, is that on some version where you discretized?
No,
Or-
no, it's actually the at least some subset of the locus of nonlinearity is this bent hyperplane arrangement that I was referring to last time. So it's really the pre-images of the 0 sets of the neurons, the non-input neurons. And not all of those are actually loci of nonlinearity, because sometimes affine linear maps can coincide when you don't expect them to, but they're at least they at least contain the locus of nonlinearity. Okay. So it actually turns out that the right language for formalizing everything that we've been talking about can be found in the dissertation of this guy named Brunert. And this was also, I think, from the 2020s, but it's called piecewise linear Morse theory. At earliest, it was like 2016. So I'll send out a link to that if you're interested. But here's the first definition. Okay, so we talked about polyhedral complexes last time. So suppose you have a polyhedral complex sitting inside of Rn. Remember, this is made up of finitely many polyhedral sets. When they meet in a common base. So let this be a polyhedral complex. Then a continuous map Rn to some other RR, say, is said to be linear on the cells. So remember, when I say a cell, I just mean one of the polyhedral sets in the complex on the cells of C. If whenever you restrict F to a cell, it's affine linear. And then here's the definition from this is kind of the key definition that makes everything go formally. So let's see. Polyhedral complex. And F from Rn to R linear on cells. And now suppose you have a polyhedral complex inside of the codomain. Then the so-called level set complex associated to this triple F, C, R. So it's just what you might expect it to be. You basically pull back the polyhedral sets in R, the cells in R, via F, and intersect them with the cells in C. Okay, so this is just the set of S intersect F inverse of Y, such that Y is a cell in R.
About this notation, on the left-hand side, it seems like I'm seeing it right, like you don't explicitly denote F. So
Yeah.
F sort of like.
Yeah.
Implicit slash you're really working with one of them, it's sort of clear given what R is.
Yeah, no, I agree that that's not great. But this is the notation that's in the dissertation. Yeah, I don't like that either. Oh, sorry, yes, for all Y and R and S and C. And so for each cell in C and each cell in R, you pull back the cell in R and you intersect it with S. Okay, but, okay, and it turns out that this is a polyhedral complex. But what's not great is that the cells are not kind of uniquely specified by pairs. Sometimes you can have two different pairs giving the same cell. And that was sort of what I was referring to last time. So let me just write at least down the statement. Although I'm not going to. This is also a polyhedral complex, and you can actually think of it as being like a subdivision of the original polyhedral complex, because each cell of this new one is some, it's an intersection of one of these cells with something else closed, something else that's closed. Polyhedral complex, which can be viewed as a subdivision. And let's say,
I'm supposed to go to R to the R.
yes, did I not do that? Yeah, here, yes, thank you. See the narrative on the 2.5. So there's this dissertation called PL Morse theory. If you look at lemma 2.5, this is essentially what this is saying. Okay. So let me give you an example. Because again, this sounds very formal, but we actually kind of already have examples in mind. I mean, it is quite formal, but we have examples in mind. So let's start with a so C is okay. So this is all right. It's a polyhedral complex, but it's a trivial one. You're just taking all of Rn as a single cell. Okay. So this is like the trivial polyhedral complex. And let's let R be this polyhedral complex inside of R up to the 1. I'll draw it. It's got 3 cells. Has 2 1 cells. So these are closed. These are just the closed intervals. From 0 to infinity and from negative infinity to 0. And then you have a 3rd cell, which is just that 0 cell. Okay. Very simple polyhedral complex sitting inside of R. And now suppose you take any affine linear map from Rn to R, then you get a level set complex in Rn. Any affine linear map. And most of the time, the pre-image of the pre-image of this 0 cell will be codimension 1. It will be an affine hyperplane. And these will be codimension 0. They will be half spaces, closed half spaces. Okay, so say, yeah. Maybe I should make that red. Maybe I should make it purple. So we've got this subdivision. All right. All right, so this is kind of a first example that we've sort of already seen. Here, let me give a more interesting example. So I'm going to define a standard polyhedral complex inside of R to the R. And it's going to have 3 to the R cells. So I'm going to write this down sort of quickly, but I'll then sketch it out in R3 so that you see what I mean. So basically for each of the R coordinates, you choose either greater than or equal to 0, equal to 0, or less than or equal to 0. So you make one of these 3 choices for each coordinate, and that's going to define a polyhedral set. And there are 3 to the R of them. And in the case of, say, R equals 3, these are just the polyhedral sets that you see. So there are the 8 3 cells, which are the 8 orthents. Those are corresponding to those choices. And then you have the various, I'll let you work it out. You can see that there are 27 cells here. You put in these guys too. 2 cells. The 2 cells are corresponding to making one of them equal to 0. The 1 cells are corresponding to making 2 of them equal to 0, etc. Okay, so there's kind of a nice standard polyhedral complex inside of R to the R for any R. And now let's do actually a concrete example. A level set complex using this. So let's let From R2 to R3. Be specified as follows. So really, I'm gonna give. So I'm gonna define weight matrix and a bias vector. That's. Really, I'm gonna write down all the coordinates. So the way that you get a vector in R3 from a point in, from a vector in R2 is you take the vector in R2 and you append a 1 to it. And then you just multiply these matrices. And then the coordinates of the output are the coordinates, are the 3 coordinates result. And we drew this picture of this situation last time, I think. I want this to be the first row. This to be the second. This to be the third row. You'll notice that the weight vectors are orthogonal to each of these. These are the 0 sets of those, the affine linear functions that are defined by the rows of this weight bias matrix. So here are the weight vectors. Or at least not the vectors themselves, but kind of attached to the hyperplanes. And so I'll let you convince yourself. Is the level set complex for R standard pulled back from R3. C is just this trivial polyhedral complex in R2. And our standard is the one that I wrote over here. You can count that you have 7 2 cells, 9 1 cells, and 3 0 cells in this complex. So quick, let's pause. There were 27 cells in our standard. Why are there only 19 here? What's going on? You have this map from R2 to R3. So you imagine this affine, that the image of the map is probably an affine hyperplane. Like it is in R3, 2-dimensional. Is it going to cut every single one of these cells? No. In fact, it only cuts 16 of them. So most of the, so you might want to try to write down all of the cells in this level set complex, but many of them are empty. But you will notice something cool, which is what I was trying to point out last time before I kind of developed the formal language, which is that if you start writing down the labels for the cells in terms of which which cells, these are pre-images of. You know, so really, you're looking at the pre-image of a cell. And you have a natural labeling of the cell in terms of a ternary tuple, +1, 0, -1. If you now start writing down those ternary labelings, what you'll notice is that for one cells, the pre-image of a one cell is a one cell. Sorry, the pre-image of a codimension one cell is codimension 1 here. The pre-image of a codimension 2 cell is a codimension 2 cell here, etc. So you start to notice that there are some nice things about this particular cell complex that you might not get in general. And in fact, this is where the fact that this hyperplane arrangement is generic is important. Let me pause for questions.
To say that again, you said codimension K when codomain matches to codimension.
Yeah, I'm gonna say all that more carefully when I actually make a definition, but I'm just kind of trying to build up some intuition here. As you start labeling these cells, you know, the natural way that we labeled them, this was like +1, +1, +1. On here, you're sort of on a decision boundary, so that becomes 0. But it's actually also the pre-image of the inner, it's the pre-image of a codimension 1 cell over here. It's where you've specified that x1 is equal to 0 instead of greater than or equal to 0 or less than or equal to 0. All right, so let me now just write down some definitions. Okay, so this allows us to define what we call a canonical polyhedral complex associated to a ReLU neural network, feed-forward ReLU neural network. Here's a definition, and this is something that I wrote down with Catherine Lindsay based on this work of Grunert. So given theta of parameter, we can define a sequence of polyhedral complexes. In each of the layers of the or a collection, I guess, polyhedral complexes. So you have this map. And now sitting inside of here, each of these hidden layers is a polyhedral complex. Okay, and RL, which is in the L minus first hidden layer, is the level set complex associated to the affine linear map. So remember, each one of these is an affine linear map composed with the component-wise ReLU. So yeah, we're for each parameter in a ReLU neural network family. You can now define these polyhedral complexes in each of the layers, in each of the non-input layers. And these are just what I just described over here. So, so the level set complex associated to the affine linear map. That complex associated to this affine linear map. So in other words, R L is C is just the trivial polyhedral complex in the domain. And R standard is what I defined before. So now we've stated formally what all of these polyhedral complexes are. But now actually we can inductively define what we call the canonical polyhedral complex, which is in the domain. And what that is basically iteratively pulling back or defining level set complexes using these. And so let me just carefully do that. Have it. So I don't think this is the way I'm stating it. I don't know if it's exactly the way that we did it in our paper. So I want to also say but the point is that you're going to define a polyhedral complex for any depth network. Okay, so if you have a depth 1 network, it's just what I described. This is just R1. Okay. And if you have, and now if you have a depth 2 network, you're going to iteratively define a level set complex by pulling back the level set from the next map. So this is the level set complex associated to F1. But where you're pulling back the cells of R2. And here, this is since F1, and this is something you should check. So now F1, which is the composition of your affine linear map with ReLU, the component-wise ReLU, is actually affine linear on cells. And you just keep doing that. So the canonical polyhedral complex associated to a composition of L layer maps is just the level set complex So you have this polyhedral complex that you've already built from the first L-1 layers. And then you just make it a level set complex for the following. For the polyhedral complex associated to this hyperplane arrangement, this linear one.
To understand it, it seems like this is the courses. There's a reason why you took this the trivial one and not at each layer you're taking this R to whatever dimension
Right.
that level is. Is there a reason you're not using the standard one, which has
Well, so let's see.
all of them? It seems like that would be finer. You just don't need it.
I guess that's the fairest way to say it. I just don't need it. I mean, we only need that to define these polyhedral complex associated to each layer map. And then once we have them in each of the layers, then we can inductively build a level set complex. But yeah, we are using that standard one where we define these ones that are in each of the layers. So let me just, this is, again, it sort of seems like maybe more machinery than we need. But it actually is kind of just the right formalism for this. So in this architecture, R2 to R3 to R. If you just look at the first layer map, you have this arrangement of 3 hyperplanes in R2. And in fact, you also have all of these cells, which are pulled back from the standard polyhedral complex in R3. And so that's what we see here. And then we have a hyperplane in R3 corresponding to this layer map. And when we pull it back, well, the kind of general case is that, well, here's one way it could look. And if we were to kind of draw what's happening in each of the layers, I guess maybe I should do that so that you can kind of see. I drew this picture last time that the labelings by these ternary signs kind of tells you where the cell goes under the ReLU network map. So if this triangle is labeled +1, +1, +1, then it will map to a triangle in the non-negative orthant of R3. And then some of these will get mapped to these 1 cells, these faces of the non-negative orthant. And then others will get mapped to the 2 cell faces of the non-negative orthant. And now if you have a hyperplane in R3, say it cuts the non-negative orthant like this, then when you pull it back, it will pull back to something that looks like this. These points of intersection here kind of chill out too. This is one picture you could have. There are many other pictures that you could have depending on what the hyperplane looks like with respect to the image of the first layer map.
So then is your final answer what's in green, or does it include the white?
Right, so the polyhedral complex now, for this whole architecture includes everything that you see.
All ones.
Yeah, all the lines that you see, yeah, that's right. And in fact, each of the cells will be labeled with this ternary labeling. Coming from which closed cells you're pulling back from. Okay. But you might also observe that somehow the situation that I've drawn here is kind of the general situation geometrically. Namely, if you have a hyperplane and it's intersecting some object, namely the image of R2, or the first layer map, you don't expect, for example, that this codimension 1 object is gonna sort of coincide exactly with this triangle here, right? That would be a non-general situation, an atypical situation. So the last thing that I want to do is kind of formalize that. So the last thing I want to do today is formalize that. And then once we formalize that, then we'll be ready to define the chain complex and actually work with it next time. So we can finish up next time. But now I need to just say a few words about transversality. So the kind of feeling that we have that this is the right typical case of intersections of these objects is formalized by the following definition. We need is a notion of transversality. Or PL maps, for finite PL maps, but in particular for these Roman networks. So we have probably just enough time to do this in a way that will be satisfied. So I'm just going to remind you of some definitions, and I'm just taking this from Gilliman and Pollitt. This is a differential for the next differential policy book. And I'm taking these definitions straight from there. So let's recall. We have a smooth map. Between smooth manifolds. And let's let P be a point in X. So these are smooth. Smooth manifolds. And P is a point in X. Then you have the corresponding map on the tangent spaces. Any point. So this is a linear map on the tangent spaces. This is essentially the Jacobian. Okay, and now let Z and Y. So Z is sitting in the codomain, smoothly embedded submanifold. And F is said to be transverse, or sometimes transversal, means the same thing, to Z. And we write F pitchfork Z. If if you look at the tangent space of P, and you push it forward into Y, and the tangent space at F of P of Z, this spans the tangent space at F of Y. And this is true for all the preimage of Z. A broad picture. Okay, so here's Y. Here's Z sitting inside of Y. Okay, and here's, let's say, X. We have a map. F. I'm gonna make X be a color so that you can keep track of it. So you have this image, and what you want is that for any point which intersects, so for any point which, any point of intersection between the image of X and Z, locally, you can get any point in the tangent space of Y nearby by taking linear combinations of points in tangent space of X and the tangent space of Z. Okay, so this is an example of a transverse intersection. This is an example of a non-transverse intersection, where they kind of kiss here. But yeah, one of the kind of classical facts is that transverse intersections are the sort of typical situation. If X were, say, 0-dimensional, then the kind of landing here would be non-transverse. But if you miss the image, then you're transverse. This is non-transverse. Transverse. And in fact, if the image misses Z, then that's automatically vacuously transverse, because you don't have any points in the pre-image of Z. So the kind of important fact about transverse maps is that the pullback of codimension, codimension is preserved under these pullbacks for transverse maps. So let me just write that down so you have it in your notes. I think I'm using the terminology in Gilman and Pollock, but so if F is transverse to Z, F inverse of Z is an embedded submanifold X. This is the important point. Moreover, the codimension. Moreover, it has expected codimension. So you should think of this as being like the rank nullity theorem on tangent spaces. But so all we kind of have to do is write down the right notion of transversality for these finite PL objects. So I'm just going to do that and then we'll call it a day. Here's the definition. If you let C be a polyhedral complex. And Rn. F from Rn to Rr. Be linear on cells. Let's see. And let Z. So yeah, actually, maybe I should. So here we have polyhedral complex C in Rn, polyhedral complex Z in Rr. So Z a polyhedral complex in Rr. Then we can talk about F being transverse on cells to Z. So we write F pitchfork C. The restriction of F to the interior of every cell is transverse to the interior of every cell in this sense, the previous sense. So the interior of every cell is a submanifold. So we can just use the ordinary definition. In the previous sense. So essentially, the way that we should be thinking of it is that the image of any cell, at least the interior of any cell, every cell will intersect the interior of every cell here in the expected codimension. So I'll just write that. maybe I won't write. The point is, we're just using the standard definition of transversality, just on the interiors of all the cells. And we're just making some definition, which is true for the whole complex. Or writing down some condition that needs to be true for every cell in the complex, in the finite complex. And then the definition that the last definition we need is that value network now F theta is said to be super transversal. If all layer maps, all of those. FL. Which, as we said, is linear on the maps, sorry, which is linear on the cells. The polyhedral complex up until this point. The canonical polyhedral complex. It's transverse on cells to this polyhedral complex, which is inside of here. This is the one associated to the hyperplane arrangement for this layer. So the point is that everything is intersecting in the expected codimension. That's going to be the upshot. So one thing that we get out of this definition is that every cell is indexed by a ternary labeling, as I described the first time, the last time. And the number of zeros in the labeling tell us the codimension of the cell. That's going to be somehow the important point, is that we have this canonical polyhedral complex. We would like to be able to label the cells in a really, really nice way. And this definition tells us that we can. This definition and a little bit of work from there tells us that we can. And so, yeah. We've now kind of done all of the major work that we need in order to define the complex. So next time I will define the complex, we'll get we'll work out an example, and then we'll just leave it there. But what's cool is that this complex is just completely combinatorially defined, and it really is sitting inside this cube complex. And the way that it's combinatorially defined is in terms of these ternary labelings. Okay, so let me stop there today.